Okay, so we're going to begin talking about chapter 10 today. And chapter 10 deals with, specifically in chapter 10.1, we're going to talk about correlation. And specifically, we're going to look at this notion, look at this idea of what we mean when we talk about this idea of linear correlation. So a correlation exists between two variables when one variable is somehow associated with the values of the other variable. And there are correlations that you're already comfortable with. For most of you guys know that the more you exercise, then the more calories burn. So there's a correlation between the amount of exercise you have and the amount of calories you burn. The more you study, the better you do in a test. So there's a correlation between the amount of time you study and how you do on an exam. There's also a correlation between the more screen time you have, the worse you do on an exam. So if you spend a lot of time the day before an exam playing on your computer, watching television, whatever it is, hanging out on your phone, then the worse you're going to do in the exam. And it's still a correlation. So the idea is, again, that a correlation exists between two variables when one variable is somehow associated with the values of the other. So exercise is associated with calories burned. Study time is associated with doing better on an exam. A lot of screen time is associated with doing worse on an exam. Well, a linear correlation exists between two variables when there's a correlation. There's a combination of two things. So there is a correlation between the two variables, and the plotted points of the paired data result in a pattern that can be approximated by a straight line. So the idea is that if you know that two things are correlated, in this case, exercise and calories burn, then the idea is when you go and plot some values for exercise and values for calories burned, that if there is a linear correlation, you get something that's approximately linear, something that can approximately form a line, not exactly linear, but something that's approximately linear. Now, we talked about this back at the beginning of the semester, and you guys may remember when we talked about scatter plots. And we're going to review this notion of scatter plots here. But the way that we measure the strength of the linear correlation between two variables in a sample is also known as R. So R is what we call the linear correlation coefficient. And then here's a mouthful. Another way, or another name that we call R, is what we call the Pearson product moment correlation coefficient. Wait, one more time. Pearson product moment correlation coefficient, named after Carl Pearson, who was a gentleman that that came up with this notion, or came up with this idea on how to measure the strength of correlation, of linear correlation. So I wanted to make sure that you're comfortable with some linear correlation values. And again, we did talk about this back at the beginning of the semester, so we are going to do a little bit of review here. So some things that you may remember about R, let's head over here and then I'll come back, is that, first of all, R is always a number between -1 and 1. All right, so let's go back up here. R is always a number between -1 and 1. So -1 is less than or equal to R is less than or equal to 1. R can never be bigger than 1. R can never be smaller than -1. If we say that R is equal to -1, as in this case over here, then we have exact linear correlation with a negative slope. Remember, we talked about positive and negative slopes. Negative slopes fall from left to right. Positive slopes rise from left to right. Okay, so if we know that R is equal to -1, we have a perfect line. So that is, you can come up with one line that will hit all these points. And it's a negative slope. So there's an infinite amount of lines that we can write that look like this, that have a correlation coefficient of -1. This is just one example. Similarly, on the kind of opposite end of this spectrum, R is equal to +1 means that we have, again, we have one line that can fit every single point on it. And we also know that it has a positive slope from left to right. This line rises. Okay, so -1, +1 very, very rarely happen in the real world, that you're going to get data points to fit a line exactly like this, but it is possible. So we do discuss that possibility. Now, let's take a look at this example. This is R is equal to -0.94. Okay, so what this means is we have fairly strong linear correlation fairly strong linear correlation. And notice also that it's negative because the trend of these lines are to fall from left to right. And we can draw a line that's pretty close, that hits a decent amount of these points, and the other points are only a small amount off of it. So fairly strong negative linear correlation in this example. This is fairly strong positive linear correlation, positive because these lines rise from left to right. So this has a positive slope of 0.8. Yes, at 0.85, I can't read that very well, or 0.86. So let's take a look at this next example. R is equal to 0. Why is this 0? Well, look at the shape. The shape is not at all linear. It doesn't form a line. This shape looks like it's more of like a semicircle type shape. That doesn't matter. The point is this is not a line at all. So the linear correlation coefficient is 0 because this is not at all a line. Similar with this guy here. Think about this as being 0.08, which is the same thing as saying there's really no line. I mean, a little bit of positivity because it kind of looks like these guys are going up a little bit. But again, 0.08 is pretty much close to 0 when we're talking about this idea of linear correlation. So there's almost no linear correlation in that example over there. So when we talk about this idea, again, of properties of correlation, we know that R is always a number between -1 and 1. R is positive, means we have a positive association or a positive slope, so the line's going to go up like this. R is less than 0, R is negative, means we have a negative association, we're going to have negative slope. Positive slope means as one variable rises, as one variable increases, the other variable increases as well. And negative means as one variable increases, the other variable is going to decrease. Values of R near 0 indicate a very weak linear relationship. Now again, it can be some other type of relationship as we saw above. It can be this kind of semicircle type of relationship. We could have a logarithmic type of relationship, an exponential relationship. Just means it doesn't form a line. That's all that's telling us, is that if you look at these dots from our data, it doesn't form anything that's linear. The strength of the linear relationship increases as R moves away from 0 and tend towards -1 or 1. So here's 0, here's +1, here's -1. This is a cloud right here. This is no linear correlation. This is perfect linear correlation. This is perfect linear correlation. So as we get closer and closer to 1, 0.8, 0.9, that means we're getting stronger to linear correlation. 0.5, the same thing over here. 0.5 would look a little something like this, scattered about the cloud-like structure, but you can tell that it's going in the positive direction. Same thing over here. The closer you get, -0.9. -0.9 would be something that's really close to being linear, but not exactly. A few points would be off. -0.5. Kind of cloud-like structure, but you can still tell that it has a negative slope, maybe going down like this. And again, 0 is completely scattered. So on this scale, the closer that you move to these kind of outermost values over here to 1 and to -1, the more linear that your relationship's going to be. And also the extreme values of -1 and +1 occur only in the case of a perfect linear relationship. This is only if you have exactly each point in your data can fit exactly one line, which, as I said before, is kind of rare in data, but it is possible to happen. And another thing to think about too is R is also very sensitive to outliers. So what we mean by that is that if we have this data set over here that looks almost perfectly linear, right? This guy over here looks pretty linear, and then some bizarre piece of data over there. It could take this, if you kind of ignore that, it could take this linear correlation coefficient, which would be something like 0.95. And then if you put that point back in, it could take off that correlation, I don't know, almost like a tenth or 2/10. So if you do have an outlier, some strange data, R will really be affected by it. So let's take a look at some examples below, and I just wanted to make sure that you understood approximately what values that we would get for R here. So this guy over here, strong linear relationship. You can see we can draw a line. Oh, that is not a good line. Okay, let's see if we can draw something a little bit better that hits almost all of the data values with maybe a few of them being off. I would say that this has a linear correlation of 0.98, very, very strong linear correlation. A weak linear relationship, so we can tell that this is a positive slope. It's a little cloud-like, but it's moving in a direction that we're familiar with, so we can see it's going to the right. I would call this linear correlation, I don't know, 0.60. So there is a linear correlation, but it's kind of weak. No linear correlation. We could approximate this correlation coefficient to be 0. It's a cloud. We can't tell if it's negative or positive slope if it was at all linear. Same thing with this guy too. You can tell this is more, looks like a parabola. So this would also have a correlation coefficient of 0 because this is not at all linear. Cloud, same thing, it's not at all linear. Let's take a look at some other examples. And again, I just want you to get this idea of, or this notion of being able to kind of approximate or coming up with it. This looks fairly tight over here. There's a few points that are off. I would say this is a good linear correlation coefficient of R is equal to negative 0.91. Negative because look, the slope is negative. It's falling from left to right. 0.91 because there are a few points that are off the line, right? And there's a small distance between the points on the line, but they're not very far off. They're fairly close to it. Okay, for these guys, I just want to make sure you're comfortable. Positive linear correlation, not very strong. I would call that 0. Maybe, I don't know, 0.55. Again, positive because the slope is positive. This is much stronger. I would call this 0.75, maybe even 0.8 for the correlation coefficient. And this, notice all of these points you can use to graph a line. It's a positive slope, so the correlation coefficient there is 1. Negative, right here. Negative, so I would say we would call this R is equal to negative 0.60. It's fairly cloud-like. You can tell that it has that negative structure, but the points aren't too far off from the line. No correlation, again, dots all over the place. That would be R is equal to 0. Same thing with this guy. There's no correlation. This looks like, there's no linear correlation, sorry. This looks like more like we could use an approxima to approximate, or excuse me, a parabola to approximate this. So I found this interesting real world example on the internet, and I wanted you to take a look at this. And what it did is, it's an example that compares temperature, degrees Celsius, to sales of something. And I want to see if we could do two things. If we could approximate the correlation coefficient here, and then if we could kind of use, if we could kind of look at the graph and see what could we imagine the situation or scenario from this data where it came from. So first of all, let's approximate R. Well, we know it's positive. And we know it's positive, again, if you look here from left to right, as we get higher, you can see here that these ordered pairs are going up. So this would have a positive slope if we were to sketch a line that drew this data. That is not the best line, but you get the general idea. In regards to approximating the correlation coefficient, I don't know why I put that one there, sorry, I was putting it positive. I would say a good approximation of this would be maybe 0.92. Anywhere from 0.85 to 0.95, I would be comfortable with you saying. I don't know why I picked 0.92, it just looks like a nice number. So all of these values here within this range, I think is a good correlation coefficient. Now, I want to make sure that you have an idea as to, or how you could kind of imagine where the data came from. And let's take a look here. Let's compare this data. On our x-axis, we have degrees Celsius, and on our y-axis, we have sales. Okay, so here's what's happening. As the temperature increases, let me say here, when it's 12 degrees Celsius, whatever this company is, it sells $200 worth of something. When it's a little bit more than 14 degrees Celsius, they sell like $210 worth of something. And you can see that this trend is to go up here. So I want you to think about what happens as the temperature increases. As the temperature increases, what do people do? So as it gets warmer and warmer outside, well, I could imagine this could be the sales of something like an ice cream store. Or maybe this could be the sales of a water ice stand. What else happens in the summer? Well, people buy t-shirts and tank tops, so maybe it's a tank top shop. Whatever it is, you should be able to kind of glean or get the general idea that as temperature increases, there are going to be some things that are going to increase as well. And again, this is kind of an imaginative example for you. So one thing you could say is as the temperature increases, either sales of ice cream would increase, sales of water ice would increase, sales of tank tops or t-shirts would increase. You can use your imagination. Maybe it's a sunglass store. But again, this is a good example or nice example of linear correlation. So what I want to do now is I want to get you used to sketching a scatter plot based on the information that we're given, and then being able to get some information from that scatter plot when we're done graphing it. For this example, I have a group of 6 smokers were interviewed regarding approximately how many cigarettes that they smoked each day, and then their age of death was recorded. And again, we talked back about this at the beginning of the semester, but I'm going to review this again. I want to make sure you're comfortable with it. And so we're going to sketch a scatter plot of the above information. Let's let the number of cigarettes smoked per day represent the x-axis. So this is cigarettes smoked per day. And then we're going to let the age of death represent the y-axis. So we're going to put over here age of death. So I'm going to start off with the x-axis. And again, I'm going to use my minimum value, which is 2. And look at my maximum value, which is 28, and we just want to make sure that we scale it appropriately. So this is a true 0. We're going to start here at 0, and we're going to end here at 28. And again, you guys can scale it however you deem appropriate. You don't even have to end at 28. You just have to make sure that 28 is captured. So let's do this. Let's start at 0, and we can end at 30, and let's just do them by 5s. So we know that 15 is going to be right here. It's going to be halfway through. So here's 5, here's 10, here's 15, here's 20, here's 25, and here's 30. And now let's look at age of death. So age of death, we're going to look at the minimum age of death, which is 52, and then the maximum age of death, which is 75. So we're not going to start at 0. It wouldn't make sense to do that here. The minimum value is 52. So remember, you put that little judge in when you skip and you're not drawing it to scale. So let's start with 50. Remember, we have to capture all of this data, and we can end at 75. And if you want, you can do them by 5s again. So here's 50, 55, 60, 65, 70, 75. Okay, so x-axis cigarettes per day, y-axis age of death. Let's graph these ordered pairs. Let's take a look at this first. So the number of cigarettes smoked per day and age of death is 64. That corresponds to the ordered pair 764. So I'm going to go over here to 7 and then 64, and let's drop a point right there. Let's take a look at 1559. So this person smoked 15 cigarettes a day and they died when they were 59. So we're going to go 1559, which looks like it's right around here. This person smoked 2 cigarettes a day and they died at the age of 75. So let's go to 75, which is right here. And again, this is approximate, but when you graph yours, you should get something that's similar. Not exact, right? Because we're scaling ours a little differently, but the general shape and the general trend should be the same in both of these. This person smoked 28 cigarettes per day and they died when they were 52. So here's 28 and about 52. This person smoked 10 cigarettes a day and they died at 60. So let's do 1060. There's 10 and 60. And this person smoked 5 cigarettes a day and they died at age 70. There's 5 and 70. So let's do 5 and 70. Okay, so this is a good idea as to what the scatter plot would look like. So let's take a look at part B. Based on the scatter plot above, would you estimate, based on the scatter plot above, sorry, I should say, what would your estimate of your R value be? So let's put that over here. Estimate your R value. And the next bit says, would it be positive or negative and why? So in regards to, is our R value positive or negative, I hope you can see here that we have a fairly downward trend going here. So we're gonna have a negative R value, and we know that we have a negative R value. Sorry, so R is negative. We know that we have a negative R value because our data is falling from left to right. As cigarettes per day increase, life expectancy decreases. Now, I made this data up, but you can imagine that something like this would be true, right? The more cigarettes that you smoke, the more cigarettes that you smoke per day, the less that you're going to live, or the younger that you're going to die. So, so we said, okay, so let's estimate a correlation coefficient for R. I would say a good estimate for R would be R is equal to negative 0.88. It's fairly strong. We hit most of that data, right? A few of these data points are a little bit off, but this is a nice estimate. Now, what we're going to talk about in a few minutes is in regards to these estimates, how do I know if I'm close or not? You won't have to worry about that, because in a few minutes, we're going to show you where these correlation coefficients come from and where these values, how we get these values. But for now, just be comfortable with the fact that R should be negative. And if you guess anywhere between negative 0.90 and negative 0.70, I would be fine with that answer. All right, so read the following sentence and circle the correct answer. As the number of cigarettes per day increases, cigarettes are getting bigger and bigger. A person's lifespan decreases. So the amount that a person lives is getting smaller and smaller. Okay, so let's take a look at this next example, which says, well, as I said before, where does R come from? Well, in order for us to figure out R, we actually have a formula for it. And here's the formula for R. Now, it's a big formula. It's an intense formula. It's not too bad in terms of calculating, but you just have to be really careful when you're plugging things into your calculator to make sure you don't make a mistake, because one plugged in incorrect value could throw you off forever. So let's do this. Let's read over the formula, and the formula says that R is equal to, R is Pearson's moment correlation coefficient, N times some xy minus some x times some y. Now let's make sure we know what these N's, x's, and y stand for. Well, N is your sample size. How many ordered pairs do we have? In the example of the cigarettes that we just did, if you want to figure out how many ordered pairs you have, you just count how many dots are on the line. So we have 1, 2, 3, 4, 5, 6. Or remember when we were converting these into ordered pairs, here's 1, 2, 3, 4, 5, 6. So N represents your sample size, or how many coordinates, how many ordered pairs that you have. X represents the values for X's, whatever value we ask you to use for X's. And it's unimportant which one you call your X and which one you call your Y here. It will become important in the next chapter. But the idea is that X represents the values for the X variable. So 7, 15, 2, 28, 10, 5. Y represents the value for the Y coordinate, 64, 59, 75, 52, 60, and 70. And the general rule is when we figure out what R is, we approximate R, we make sure that we round it to 3 decimal places. Just like in Z values, we always round to 2 decimal places. For T values, we round to 3. For R, we always round these guys to 3 decimal places. So for this example, make sure you have a calculator on you. Let me go grab my calculator. And for this example, we're going to use the formula for R to compute the exact value. So as we kind of saw before, you can graph these ordered pairs and approximate what R is, right? And I said for this example, R is equal to negative, my approximation was R is equal to negative 0.88. And I should probably do this. It means it's approximately equal to and not exactly equal to. But what we're going to do now is we're going to figure out the exact value. So the approximation is what happens when you graph the points and you look at it and you say, okay, it's kind of linear. It's a positive or a negative slope, and you give it a value that you think would represent it well. That's an approximation. This is how we find the exact value for R. So what we're going to do is we're going to talk about how we can use this formula to compute the exact value for R. Now what we are going to do is we are going to use something similar to the column method that we used before. We're going to have a column for X's. And you've seen this column method. We used it for standard deviation. We're going to have a column for Y's. We're going to have a column for XY. We are going to have a column for X squared. And we are going to have a column for Y squared. Now you just have to be careful when you're putting these values in here that you make sure that you pair them up appropriately. So notice that this person that smoked 7 cigarettes per day died at the age of 64. You have to make sure that you pair 7 and 64 together. That becomes important for this step over here. This person smoked 15 cigarettes a day and they died at 59. This person smoked 2 cigarettes a day, they died at 75, 28 and 52, 10 and 60, and then 5 and 70. And again, just make sure you actually pair them next to each other. So for each one of these columns, and we'll come back to the formula. For now, I just want to make sure that you're comfortable with the column method. For each one of these columns, okay, so this third column over here says XY. So you're just going to multiply the X and Y value of your coordinates together. 7 times 64 gives us 448. Okay, this column over here, so let's just do the whole X column, the XY column first. The next one's 15 times 59, which is 885. 2 times 75, I don't need my calculator for that one. 28 times 50, 2. 1456. 60 times 10. And 5 times 70. That's 350. Let me just go back and double check. I want to make sure I don't make any mistakes. 448, 15 times 59, 885, 2 times 75 is 150, 28 times 52. 1456, 10 times 600, and then 5 times 73. Good. Okay, the next column is X squared. So you're going to take this value and square it. So 7 squared, 49. Take this value and square it. 15 squared is 225. Take this value and square it. 4 squared, 2 squared, 2 times 2 is 4. Take this value and square it. 28 squared is 784. 10 squared is 100. And 5 squared is 25. Okay, so these are all these columns squared. And then we're going to do the same thing for the Y squared. And so for our Y's, we're going to square all these values. So 64 squared, that's 4,096. Some of these numbers can get pretty big because if you have big numbers to begin with and you're squaring them, they're going to make them pretty big, but that's okay. Don't be scared. 75 squared. 5625, 52 squared, 2704, 60 squared is 3600, and then 70 squared is 4900. So this is all of the information that you need, these values over here. I'm just going to cut this off and erase this little, no, I don't want to do that. Okay, oops, sorry about that. Let's go back up to this guy. So here's how I want you to think about this. I'm going to go back up here to the formula, and what we're going to do is we're going to plug these values right into the formula that we were just looking at. Sorry, again, this guy's just skipping around right here. It's not happy with me right now. No. Okay, so I'll just leave that alone because I don't want to spend all my time playing with this over here. All right, so what I want to make sure that we're comfortable doing is plugging this information into the formula. So let's get this information into the formula. And here's how we're going to handle it. R is equal to, I'm going to take these values that we have over here and start plugging them in. Well, R is equal to, let's take a look in the numerator, N. Now remember, N represents the number of ordered pairs that we have, and we have 6 ordered pairs. Okay, N times the sum xy. Now we have a column for xy, and remember that this sigma over here means the sum, so let's add those values together in that column. We have 448 plus 885 plus 150 plus 1456 plus 600 plus 350, and that gives us 3889. Put that in there so don't forget it. So this is 6 times 3889 minus sum of x, so that means we're going to take our x values and sum them up. We have 7 plus 15 plus 2 plus 28 plus 10 plus 5. That gives us a total sum of 67. Okay, let me just check my math one more time. Okay, looks good. So sum of x is equal to 67 times the sum of y, and now let's add up the y values. We have 64, 59, 75, 52, 60, 70, and that's 380. So that's times 380. And this will tell us what is in the numerator. So let's do that over here. Let's write down what's in the numerator. So in my calculator, I'm going to hit 6 times 3,889 minus 67 times 380. You're going to type that whole thing right into your numerator. And I get negative 2,126. So that's the value that's in our numerator. And we have to do the denominator next. And the denominator is a little bit more intense. Again, just because a decent amount of computation that's going on here, n. Okay, so remember, n is the number of ordered pairs that we have, and we have 6 of them, times sum of x squared. Okay, sum of x squared. So that means we're going to take this column, the x squared column, and sum those values up. 49 plus 225 plus 4 plus 784 plus 100 plus 25 gives us 1,187. Minus. Now this is tricky, be careful. Notice that the 2 is on the inside, so this really is the sum of the x squared values. This second bit of the formula says the sum of the x values quantity squared. So we already know what the sum of the x values are from this. It's 67. So this is going to be minus 67 quantity squared. Okay, then I'm going to close that off. That's that first bit of computation. So 6 sum x squared comes from this column, minus sum x quantity squared. So the sum of, this sum x squared comes from this column, 1,187, 6, 1,187, minus this bit, sum x quantity squared, comes from this value, quantity squared. Okay, so that's times. Let me drag this guy out for a little bit. Let's do this a little bit. N, which again is 6 ordered pairs, sum y squared. Okay, so we don't know what the y squared values are yet, so let's figure out what the sum of the y squared values are. We have 4,096 plus 3,481 plus 5,625 plus 2,704 plus 3,600 plus 4,900, and I get 24,406. So this is 6 times 24,406 minus some y quantity squared. So now we're going to go to this bit. The sum of our y values are 380. So we're going to do 380 quantity squared. Okay, so the denominators are a little bit more intense. So here's how I suggest that you handle the denominator. We already know that the numerator is going to be negative 2,126. For the denominator, let's do this. 6 times 1,187 minus 67 squared. So in my calculator, I'm going to type in 6 times 1,187 minus 67 squared. And remember that squaring something is multiplying it by itself. And I get 2,615. I'm going to multiply that by 6 times 24,406 minus 380 squared. And remember, when you square a number, you're multiplying it by itself. So you could also call it minus 380 times 380. And there I get 2,036. Okay, so again, the numerator, I'm not going to play with the numerator. Let's just continue playing with the denominator. This becomes, in the denominator, the square root of 2,615 times 2,036. And when you put it into your calculator, you're going to do it like this, 2,615 times 2,036. So put parentheses around the two of them. So the square root of 2,615 times 2,036. And I get 2,307.4098. Now, the quotient of these two is going to tell us what our correlation coefficient looks like. So when we divide them, that's what we're going to get for our correlation coefficient. Negative 2,126 divided by 2,307.4098. And we get negative 0.92. Okay, so we get negative 0.92 for our correlation coefficient. We knew it would be negative. And we go back up here. Oh, not too far off, right? Look what we said. I guessed that it was negative 0.88, and it ended up being negative 0.921 using the formula. So not too far off from guessing. And as I said before, sorry, I should make sure that you do this correctly. Negative 0.921, we're going to round R to 3 decimal places. So it would make sense, again, that we have a negative correlation coefficient. These ordered pairs are moving down from left to right. So we have a negative slope. And this is how you compute the correlation coefficient. So let's talk about a quick definition, and then we'll do one more example of this. There's a definition that's called R squared. R squared literally just means what happens when you square the correlation coefficient. And the value of R squared is the proportion of variation in Y that is explained by the linear relationship between X and Y. So I wanted to give you an example about that, and here's the example. If the relationship between two variables, so let's say we have two variables are X, Y, where X is the amount of sleep you get before your exam, and Y is your final exam grade. So let's say we computed the correlation coefficient for this, and we end up with a value of 0.801. Then R squared is equal to 0.801 squared, which is the same thing as saying 0.642. Okay, so 0.642, if we convert that into a percent, pick up the decimal and move it 2 places to the right, we get about 64% or 64.2%. So the information that this tells us is 0.642 or 64% of the variation in the amount of sleep you get can be explained by the linear relationship between sleep and the final exam grades. So we can explain away 64% of your exam grades due to the linear relationship in the amount of sleep, which means that we can't explain 36% of it from their linear relationship. There's other factors going on here. How much did you study? How healthy did you eat before the exam? How many classes that you skipped? So that's what that 36% means. So anytime you hear R squared, literally what you're doing is you're taking Pearson's correlation coefficient and multiplying it by itself. And that will tell you the proportion of variation in Y that's explained by the linear relationship between X and Y, where X and Y are your coordinates, whatever coordinate values you're working with. Okay, so one more example, and then we'll call it a section. And so what I wanted you to do is to, oh, there we go. What I wanted you to do is I wanted you to get a real world working or a real world understanding of the correlation coefficient. And this comes from something that's called Dolbear's law. Now, Dolbear's law, there's a very interesting scientist who's a natural scientist. And what Dolbear did is he noticed that you can approximate the temperature based on the amount of times that a cricket chirps per minute. And this is a true scientific phenomenon. If any of you head out of the city in the summer, if you can make your way into the suburbs or the country, you'll hear crickets chirping at night. And depending on the species of the cricket, you can approximate with fairly fairly decent accuracy what the temperature is going to look like outside. And I put a link up here for any of you who want to check and read about Dolbear's law in case you're interested in it. So a cricket that chirps 55 times per minute is predicting that it's 50 degrees outside. A cricket that chirps 67 times per minute is predicting the temperature to be 54 degrees outside. 75 times per minute is predicting a temperature to be 55, 99, 60, and so on and so forth. You get the general idea. So let's talk about, first of all, how we could sketch a scatter plot that represents this graph. Ooh, that is not a great straight line. That's actually a terrible straight line. So let me do that one more time. Really? That's even drunker than the first one is that we just had here. There we go. And there you can tell I'm getting more and more tired. Let me try that guy one more time. Okay, a little bit better. All right, so let's sketch the scatter plot of this graph. Let chirps represent the x-axis and temperature represent the y-axis. So in regards to chirps, we're going between 55 and 178. So I'm not going to start at 0. I'm going to take that little leap over there. Let's start at 50, and let's do it up to 180. And let's do it by tens. And that makes sense. Let's do 50, 60, 70, 80, 90, 100. 110, 120, 130, 140, 150, 160, 170, and let's just move 180 over to have it not have such a giant gap in it, and then we'll have 180 over here. Okay, for the temperature, so over here, this is degrees Fahrenheit. For the temperature, I'm sorry, this is the chirps. This is the number of chirps. For the temp, so over here, this is degrees Fahrenheit. The temperature is starting at 50 and going up to 79. So again, let's do the judge to show that we're not using 0 as our true starting point. We're going to start at 50 and go up to 79. So let's do from 50 to 80. And we can do it in terms of fives. 55, 60, 65, 70, 75, 80. All right, so let's sketch a scatter plot that represents this. Let me use another color for the scatter plot here. I'll use a regular pen too. I'll go over to here and I'll use a regular pen. Oh, Jesus, beautiful blue to represent that. Okay, all right, ready? So this first ordered pair, when a cricket chirps 55 times per minute, the temperature is 50 degrees. So this is our starting point where it is right over here. When it is 67 degrees, a cricket chirps 54 times per minute. When it's 75 degrees, excuse me, when a cricket chirps 67 times per minute, it's 54 degrees. When a cricket chirps 75 times per minute, it is 55 degrees. Let's do 75, 55, a little bit higher than that other guy. When a cricket chirps 99 times per minute, it's 60 degrees. So let's do this, 99, 60. When a cricket chirps 119 times per minute, so a little bit less than 120, it's 67 degrees. Let's go 65, 66, 67, right around here. When a cricket chirps 134 times per minute, it's 69 degrees. 149, it's 74 degrees, so 149, 74, all these numbers ending in nines over here. And then 178, 79, so 178 would be right there, 79 would be right right around there. Oof, fairly tight linear relationship. So here's what a scatter plot of this graph would look like. Estimate R and write a statement that describes what happens to the number of chirps as the temperature rises. Okay, so the first bit, estimate R. I mean, looking at this, I would say R is equal to 0.95. Positive because it's rising from left to right. Very close to 1 because it looks like we could draw a line that captures almost all the data, and even the data points that are off of it, they're going to be a little bit off of it. But remember, this is an approximation. This that I drew and this, these are approximations. And the second bit says, write a statement that describes what happens to the number of chirps as the temperature rises. So as the temperature increases, so does the number of chirps per minute. Okay, so the next bit says, use the formula above to find the exact value for R. So what I'm going to do is I'm going to go and cut and paste that formula that we had before. Sorry, let me do this. Let me cut this guy and let me copy this guy. Let me paste it over here. Okay, so here's what the formula looks like. And off to the side, I'm going to create the chart that we did before. X, Y, X, Y, X squared, and Y squared. Okay, so let me get my coordinates over here too. 55, 50. All right. 67, 54. Sorry, I'm going to make you a little nauseous bouncing up and down. 75, 55. 9960, 11967, 13469, 149, sorry, 149.74, and 178.79. Okay, now we also know for all of these that we're going to need the sum, so I'll just put the sum of these values in this last box over here. I'll just call these the sum. That guy's going to go over here. Let me do the sum of the x values first. So when we add together all those x values, 55, 67, 75, 99, 119, 134, 149, plus 178, we get 768. When we add together those y values, 50, 54, 55, 60, 67, 69, 74, 79, we get 508. And give me 1 second, I'm just going to double check my work here. I want to make sure I don't make any computational errors. Oh, okay, look, the first guy, let me double check. So 55, 67, 75, 99, 119, 134, 149, 178, 876. Oh, see, that's why I check. I actually ended up getting 876. let me double check 876. 178 minus 149 minus 134 minus 119 minus 99 minus 75 minus 67 55. Good, so that column looks good. Let me check the y values also. And we get 508, looks good. Okay, so this next column is xy, so I'm just gonna take these two values, multiply them together and write them there. So 55 times 50 gives us 2,750. 67 times 54, 3,618. 75 times 55, 4,125. 99 times 60, 5,940. 119 times 67, 7,973. 134 times 69, 9,246. 149 times 74, 11,026. And then 178 times 79, 14,062. Okay, and then again, let's add all of these guys up. 14,062 plus 11,026 plus 9,246 plus 7,973 plus 5,940 plus 4,125 plus 3,618 plus 2,750, and I get 58,740. Okay, so that's for the sum of my xy column. Now x squared, we're going to take each one of these values, square it, and then write that in this column. So 55 squared, 3,025, 67 squared, 4,489, 75 squared, 5,625, 99 squared, 9,801, 119 squared, 14,161, 134 squared, 17,956, 149 squared, 22,201, 178 squared, 31,684. Okay, so again, I'm going to sum up this column and see what we get here. So 31,684 plus 22,201 plus 17,956 plus 14,161 plus 9,801 plus 5,625 plus 4,489 plus 3,025. Let me just make sure for 3,025, 4,489, 5,625, 9,801, 14,161, 17,956, 22,201. Okay, and I get 108,942. And then let's do one more. We're going to do for the y squared. We're almost there. You guys are doing great. Okay, so y is 50. Y squared is 2,500. 54 squared, 2,916. 70, see, this is 55 squared, 3,025. 60 squared is 3,600. 67 squared, 4,489. 69 squared, 4,761. 74 squared, 5,476. And 79 squared, 6,241. Okay, and again, I'm going to add up these values, and then we're done the hard part. Now, the substituting in is the fun part, but the computation is the hard part. So 6,241. Like 6,241 plus 5,476 plus 4,761 plus 4,489 plus 3,600 plus 3,025 plus 2,916 plus 2,500, and we get 33,008. Okay, let me just double check. Okay, looks like it works out. All right, so let's substitute in. So R is equal to, in the numerator, N are the number of ordered pairs. We have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 ordered pairs times some XY. So here's XY. Sum XY is 58,740 minus sum X. So here's sum X, 876 times sum Y, which is 508. Okay, so that will tell us what is in the numerator. Let's see what we get in the numerator. And again, I'm just going to plug this straight into my calculator. So 8 times 58,740 minus 876 times 508, 24,912. Okay, denominator, square root, big square root. See this guy? Big square root. N, which again is 8. Okay, times sum x squared. Well, we know x squared is over here, so the sum x squared is 108,942 minus sum x, which is 876, quantity squared. Okay. And then we're going to do the same thing for the y's. So I'm just recopying the numerator over here because the denominator is going to be taken up by this guy. N, which is 8, times sum y squared. So here's y squared. Sum y squared is 33,008. Minus sum y, quantity squared, so that's minus 508 quantity squared. Okay, so here's what I'm going to do. I'm going to figure out what each one of these little bits are equal to, and we reduce them down to just 2 factors. 8 times 108,942 minus 876 squared, and I get 104,160. Okay, so the second bit is 8 times 33,008 minus 508 squared, and I get 6,000. Okay, let me just double check. 8 times 108,942 minus 876 squared. Looks good. 8 times 33,008 minus 508 squared. Looks good. We get 6,000. Okay, so I'm going to put this quantity over here into the square root. Remember, my numerator is 24,912. So I'm going to put the square root of parenthesis 104,160 times 6,000. And I get this, I get 24,999.199. Okay, so remember, it's the quotient of these two which gives us R. So the last thing we're going to do is divide those two. And then we're going to round the answer to 3 decimal places, 24,999.1999. And we get 0.997 rounded to 3 decimal places. So there is a very strong linear correlation between the temperature outside and the amount of times that a cricket chirps per minute. And this is the exact value for R. Now, the last question says, interpolate the data. If a cricket chirps about 140 times per minute, what is a good estimate as to what the temperature is? So when we ask you to interpolate something, that means we're going to look in the range of the data that we have. So if a cricket chirps 140 times per minute, so that means assuming that we are using this data, here's 140, let's come up with a good approximation for what the temperature would look like. Here's 140, looks like this point's on the line. And if we go across here, it looks like the temperature would be right around 74 degrees. A little bit less, maybe 73, 74 degrees if the temperature, excuse me, if the cricket chirps 140 times per minute. So what you do, if we're asking you to interpolate some of these, you look inside the data, you realize it's a linear trend, you put it on that line, and then you try to use that to help you figure out what this could be, maybe 73 degrees outside. So what we talked about today is we talked about how to do a scatter plot, how to approximate R, and then how to use a formula to find the exact value for R. Now we also talked a lot about this idea that there is a line, if you have data, that there is a line that you can use to best fit the data. I was drawing in pictures of lines, but it turns out that we do have, assuming that we have a nice linear correlation between two variables, that we can figure out what the equation of the line is that best fits the data. And that's what we call linear regression. But we're going to save that for the next class. So again, for today's lesson, I want to make sure that you're comfortable with the following information. I want to make sure that you can do a scatter plot. So number one, a scatter plot. Number two, that you can approximate R. Tell me something about it. Tell me, is R positive? Is it negative? Give me a good approximation of values. Tell me information about the graph or the scatter plot, and then find the exact value for R. All right, so I'll see everybody next class when we talk about the line of best fit, which is chapter 10.2.